In today's video, we will take a look at Adadelta, a variant of stochastic gradient descent that, like RMSProp, solve the shortcoming of Adagrad. We'll look at the formula and then we will dive into the code. As shown in the previous video, Adagrad is a variant of stochastic gradient descent that adapts automatically the learning rate. The main problem with it is that as the training goes on, because we accumulate gradient, the learning becomes slower and slower until it just stops. To palliate to this, Adadelta uses a running mean over a certain period of time. It can forget the past. So the formula looks like this. If you saw my RMSProp video, it is fairly straightforward as the two methods share similarity. So let's break it down. Here we have theta t plus 1, which is the new value for a given parameter. We have delta at t, which is the current value. We have a delta of theta at t. So this is how much we want to change the parameter, right? And delta at theta at t is the formula at the top. Here we have the gt over here. This is the gradient at time t. RMS g at time t is equal to this other formula. So there's a lot of formula to unpack. We're going to go one by one. So it's equal to that thing. And we saw the same thing in RMSProp. Here, E over here is epsilon. It's a number for numerical stability in the division so that we don't divide by 0. This E at G to the 2 is the same formula as we saw in RMSProp, which boiled down to that thing. So let's break this down also. So this is the running average. This variable is the decay factor, and it's usually set to 0.9. We have E at G. E of g to the 2 at t minus 1, which is the past average. And over here we have g exponent 2 at t, which is the gradient squared. So this is pretty straightforward. This is a running average. And we just need to pack it up all the way up until RMSGT. So going back to the second formula, we have that thing, which is the root mean square of the delta at t minus 1. So it's similar to the one that we saw before. So we have this, epsilon is still the same thing, and we have this E at E of delta of theta exponent 2. And this is still a running average, so we have this formula. So here, this is still a decay factor, this is the previous running mean, and this is the past update squared to the 2. So if you look carefully, we have RMS of delta theta at t minus 1, not at t, in this formula, since it's a value we don't know yet when we're doing this current update. So we approximate what it should be by looking at the previous operation, and then once we update theta at t plus 1, then we can calculate delta at t. So this might look complicated, but it's fairly straightforward to implement. So let's take a look at the Python code. Good, so we're going to take a look at an implementation of Adadelta. Like always, we're working on the same notebook as before. It's the same setup. I'm saying this because we've done those past optimization algorithm. So RMSProp is really similar. Now we're going to look at Adadelta. The setup, like always, it's just a linear function we're trying to optimize using stochastic gradient descent. So there's going to be just two parameters. So it's just a dummy setup so that we can just do a sanity check on the code. So if you want to know more about the setup over here, just look at my past video with RMSProp. We're just modelizing a line with two parameters, and those are the derivatives that we're using to calculate the gradient. Those are partial derivative, and this is just a helper function to get a stochastic sample. There's nothing inherently difficult with those. We just need to take the time to go through it. So let's take a look at let's take a look at the setup. Here we have the first setup, which we want to see if we can have w0 equal 0 and w1 equal 1. So we set up those fake data. So we have it's literally a line with a slope and no intercept, so it intercept at 0. And this is what will be fed to the optimizer with the model that we need, and the model is a line. So that's what we're doing. So we're doing it for all of them, and this is Adadelta. We're doing the same thing with an intercept of 0 and slope of 2, and an intercept of 1 and slope of 2 over here. So that should work, but let's look at the code. So here, this is Adadelta. We have a model. So this is a line, could be anything else. We have our x, our y's, the decay factor, which is hard-coded at 0.9, the maximum number of iterations that we want, and the epsilon that we saw before. This needs to be a really small number. It's just here for numerical stability. It shouldn't impact the learning. So if you remember, there's two running average that we need, and we need to keep track of delta. So delta of the parameters. So here, remember, we have two parameters. We have w0 and w1. So this is for w0, this is for w1. Same thing for all of them. Here we're not using a numpy array. We're just using a simple list, just so that we can visually see what's happening. So this is the expectation for the gradient. This is for the parameters, and this is the delta at p. And this is the training loop, right? All of this. It's fairly small, and over here, this is where we print the iteration. So there's nothing here really to see. The whole algorithm sits over here. So the first thing you do in every iteration is you select an x and a y. This is the stochastic part in stochastic gradient descent. So Adadelta is still a stochastic gradient descent based algorithm. Here you calculate the gradient, so you calculate g0 and g1. Those are partial derivative, right? So if you look at the model over here, right here, this is a partial derivative of the line formula, this one. So we get this thing for w0 and this thing for w1. It's pretty straightforward. So once we get the gradient, this is where we're going to update the stuff. You see I've unrolled it, so just so that we can visually see better. There's a lot of improvement over here that we could do and over there because of the hard-coded W's and W1, but this is for illustration purposes. So we have the decay factor. Remember, we saw it over there. It's 0.9. It's used over here, and then this is the current expectation at G, and this is the still the current expectation at G for W0 and for W1. So we're doing the same thing for all the parameters, and this is the gradient squared. So this get the new running average for the gradient, and here we get the new running average for the parameter. Remember the parameter, there's something a bit weird with the delta p that is happening. We don't update the delta p before we calculate this. We have to use the previous one, like EP and AG over here. While the G, we don't use the previous one, we use the current one, right? So this is the t-1 thing, because this, you cannot calculate it yet. You don't have all the information. To calculate this, you need this and that. So yeah. So this is the same thing as this. It's still a running average, and we update EP at 0 and EP at 1. That's it. And after that, this is where you calculate the gradient, right? So remember, this was this formula that we saw with the RMSProp, the RMS for EP and RMS for EG. Those are the two things. So this is RMS for EG, and this is root mean square for EP, and this is the gradient. That's it. And we do the update, and the update is super simple. It's the previous W0 plus how much we want to change it. And that's it. And honestly, there's nothing very difficult about this. Let's look at if this thing can actually learn something. It's still running, yes. Okay, so I should just disable the other one. So this should be Adadelta. Yes, it's Adadelta. It starts random values, and then this should go to 1, and this should go down to 0. And you see after like 1,000 iteration, it's almost there. I make it go until 10,000, and it's getting pretty good. Yeah, getting pretty good. That's it. That's the right value. So the optimization is working. If we look at the other one with the intercept of 0 and the slope of 2, we also do get something that is very close to 0 and something that is very close to 2, right? And same thing for an intercept of 1 and a slope of 2. Hopefully. Yes, intercept of 1 and a slope of 2, and that's it. There's nothing difficult about this algorithm. Just like it's looking very similar to RMSProp, except that you have those two that are added compared to RMSProp, which is just look at this one, E expectation of G. So alright, I hope that you have enjoyed today's video. If you have comment or question, don't hesitate to write them in the comment section, and like always, have a great week.